Good morning, everybody. In this lecture, I would like to discuss the basic concepts of stresses and strain. The topic falls under the subject strength of materials or mechanics of deformable bodies, which deals with the relationship between internal forces, deformation, and external loads. The concepts covered in this lecture are basic concepts of stresses and strain, loading and deformation of bone structure. Now, let us first consider a simple spring mass system. If a weight of mass m is hung from the end of a spring, the spring undergoes an elongation of x. If the weight is doubled, the elongation increases to twice x. So, the solid bodies deform when they are subject to external forces. They are either compressed or stretched or bent or twisted. They can actually maintain their shape to some extent or lose their shape as well. Hooke's law of elasticity actually states the relationship between the displacement and the deforming forces. For relatively small deformations of an object, the displacement is directly proportional to the deforming force or load, which can be written in the form F is proportional to x or F is equal to kx. The proportionality constant k is known as the stiffness of the material. The stiffness is a property of a material by which it can offer resistance to deformation. How do we define stress? Stress is the internal force per unit area generated within a material when it is acted upon by external forces. In compression or tension, uniaxial of course, the normal stress sigma is the ratio of the resisting force to the cross-sectional area as shown in the slide. It should be noted here that we can apply forces, not stresses, on a body. Stresses are actually generated within a body. And most importantly, the definition of stress is associated with orientation of the area on which it acts. Next comes strain. When a cylindrical bar is subject to external tensile force at one end, it may undergo slight increase in length and decrease in diameter. The change in dimension is known as deformation. The average linear strain is the ratio of the change in length to the original length. So, strain is deformation relative to the size of an object. The displacement compared to the original length is a measure of strain epsilon. So, it is basically measuring a fractional change and it is a unitless quantity. Normal strain is a measure of change in size, whereas shear strain, which is an angular measurement, is a measure of change in shape. Strain, therefore, is more fundamental than stress, because without a strain, stresses cannot be generated within the body. Now, let us discuss about the stress strain curve. The stress strain curve can be plotted from the data obtained from a tension test. So, herein we plot the stress strain curve corresponding to a ductile material. So, there are few important key points in this curve as well as two distinct regions. The curve can be divided into an elastic region and a plastic region. The material which is stressed in the elastic region returns to its original configuration when the load is withdrawn. However, the deformation obtained in the plastic region is irreversible. In the plastic region, the material undergoes permanent deformation. The linear elastic behavior of material actually lasts up to a limiting point corresponding to yield strength or yield stress at indicated as point A in the graph. The maximum stress that a material can withstand while being stretched before breaking is known as the ultimate strength indicated by point B. For an even higher strain, the material will break or fracture at point C as indicated in the graph. In the lower stress strain region of the curve, linear elastic behavior is exhibited, which implies that the strain is directly proportional to the stress, contrary to the nonlinear behavior in the plastic zone. The proportionality constant in this linear elastic zone is actually the tangent of the angle subtended by the linear part of the curve with the strain axis, and this proportionality constant is known as the Young's modulus of the material. So, Young's modulus can be actually related to the Hooke's law, and finally, the stiffness of this cylindrical specimen subject to tensile forces can be calculated as EA by L. So, it is dependent on the geometry of the specimen as well as the Young's modulus. Now, let us define a shear force. A shear force acts parallel to a surface as shown in the figure, and it causes shear deformation and distortion in the solid object. So, this is the deformation, and overall there is a distortion in the shape of the solid object. Accordingly, shear stresses and shear strain can be calculated as indicated here in the slide. The shear modulus is another modulus which is analogous to the Young's modulus, and it is a very important material property. The shear modulus also relates to the Hooke's law. The angle, which is known as the shear strain, is used to measure change in shape. So, the shear modulus can be related to the Hooke's law, and the shear stresses and shearing strain are indicated here in the slide. Now, let us consider a more generalized state of loading, wherein it is indicated here in the figure that if we pull a body along the y direction, it will tend to contract in the x direction due to the Poisson's ratio effect. So, Poisson's ratio is basically the lateral contraction to the axial elongation. The stresses and strains at a point in a structure are related to each other through the elastic properties, Young's modulus and Poisson's ratio, using the generalized Hooke's law. Actually, the strain along one particular direction is not only due to the stress along that particular direction, but also it accounts for the stresses along other two orthogonal directions as indicated in the generalized Hooke's law. So, the directions of the linear strains as well as the shear strains can be calculated using the set of 6 equations. It is also important to know the relationship between Young's modulus, shear modulus and Poisson's ratio for an isotropic material. Now, what happens when a body is subjected to a set of forces and constraints in generalized form? We will consider the deformation of the solid body due to the action of the external forces and constraints. It can actually have 3 consequences. One is the contraction dilation, so it can change in its volume. Other is due to shear, which leads to change in shape. It can actually translate or rotate. That means the position and orientation can also change, but there is one option, one possibility, that a combination of all these modes can also happen. Now, let us discuss about the components of stress tensor. Stress is basically a second order tensor. A 0th order tensor is a scalar quantity, a first order tensor is a vector quantity, and a second order tensor is, for example, is stress. It is easier to understand stress in terms of its components and the effect of components in causing deformation to a unit body within a material. For defining stress, as I have indicated earlier, we need to define the orientation of the area on which it acts. The components of stresses in 2D are 4 in total, 2 normal and 2 shear stresses. In 3D, there are 9 components, 3 normal and 6 shear stresses. Let us try to understand the components of a stress tensor in more detail. So, here as you can see, the first index of the stress component actually indicates or refers to the plane on which it acts. So, here it is sigma x, means it is acting on the plane x, and the second is the direction. The second x is basically it is acting along the x direction. That is the reason we have this component is called sigma xx. If sigma is written in dissimilar subscript, it actually refers to shear stresses. So, sigma xy actually means tau xy, because shear stresses are symbolized as tau. So, in a 2D stress component, the 2D stress components are sigma xx and sigma yy, the normal stresses, and shear stresses tau xy and tau yx, which are complementary shear stresses. Now, shear stresses are responsible for plastic deformation in metals. Now, here also we can see that we have represented sigma xx or sigma 11. It means it is acting on x plane and along the x direction, whereas tau xy or sigma 12 means it is shear stress, tau yx is acting on the plane y, but along the x direction. Now, the stress is considered as a systematic tensor. Basically, according to the principle of conservation of angular momentum, the stress is a systematic tensor wherein the shear stresses are complementary. So, tau xy is equal to tau yx. The stress components in 2D and 3D system are indicated in the slide and also pictorially presented for understanding each of the stress components in the tensor. Now, the stress components can be classified as hydrostatic and deviatory components of stress. Let us first understand the concept of hydrostatic and deviatory stresses in a 2D system. The hydrostatic stress is basically the average of the two normal stresses as indicated here in the mathematical expression. It is the average of the two normal stresses. The state of stress actually can be expressed in such a way that we can obtain a hydrostatic part and we can obtain a deviatory part. Diagrammatically, state of stress represented as a hydrostatic part and a deviatory part. The hydrostatic stress causes change in volume, whereas the deviatory component of stress causes change in shape. Let us now discuss about the principal stress and some other scalar quantities that are useful in biomechanics subject. The principal stress are the maximum and minimum normal stresses in a state of stress at a point. These stresses act on the principal planes defined by the principal direction, wherein shear stresses are 0 or absent. The principal angle is the orientation of the principal plane with respect to the original axis. The von Mises equivalent stress is a very useful scalar quantity that is calculated by combining the three principal stresses. Thereafter, this value is compared with the yield stress of a material to determine failure. It is mostly useful for ductile material such as metal. Another important scalar quantity, strain energy density, is defined as the strain energy stored per unit volume of a material, where the strain energy is the area under the stress strain curve. Now, what is the relation between stresses, strain and failure? This needs to be explicitly defined. In every material has a strength expressed in terms of stresses or strain, beyond which the material fractures or fails to bear the load. So, we need actually a failure criteria to speculate failure and a theory known as failure theory to justify the failure criteria. Why do we need failure theories? To design structural and mechanical components and to calculate the margins of safety. We also need to develop new materials and to evaluate weak and strong directions. The theories of failure is required to specify the conditions under which a material can fail under the action of a set of external loading conditions. For a ductile material, failure is usually specified by the initiation of yielding, whereas for a brittle material, it is specified by fracture. Some important theories of failure and their applicability is listed here. The first is the maximum principal stress theory or Rankin's theory, which is applicable for brittle material. Maximum shear stress theory, popularly known as Tresca theory, is applicable for ductile material. Distortion energy theory or von Mises theory is applicable for ductile material. Maximum principal strain theory is also applicable for ductile material. Maximum strain energy theory, Haig's theory, is applicable for ductile material as well. Moore's theory, which is based on the Moore circle, is applicable to the brittle material. So, within this set of 6 theories, maximum principal stress theory and Moore's theory are popularly applicable for brittle materials, and maximum shear stress theory and distortion energy theory are applicable for ductile material. Now, let us consider the possible loading scenarios for a bone structure. And the consequences of these loading scenarios on deformation of the bone structure. So, the probable loading scenarios are compression as indicated here, tension, compression, tension, shear, torsion, bending, and finally, a combination of all of them acting on a bone structure is a common occurrence. So, if we consider compression, you can see that this here we have indicated small stress elements, how the stress element is deformed is indicated in this diagram as well. So, compression can cause shortening and extension, tension can cause narrowing and elongation, shear can cause a change in shape, a torsion can lead to angular distortion, and a bending mode can include all changes seen in compression, tension, and shear. So, let us list the conclusion of this lecture. Stiffness is the property of a material by which it can offer resistance to deformation. Stress is a second order tensor which requires the definition of the orientation of the area on which it acts. Principal stresses are maximum and minimum normal stresses, and it acts on planes where the shear stresses are 0. Hydrostatic stress cause change in volume, whereas deviatory component of stress causes change in shape. The possible loading scenarios for a bone structure are tension, compression, shear, torsion, bending, and combined loading, considering all of this basic loading configuration. The references are listed here. These are very popular textbooks, and I would like to thank you all for listening.